In this video, we're going to look at a few examples from Lesson 23-2 in your Springboard. And these examples are going to show us how to apply the sum and difference identities. We're going to start here with example A, which is on page 308 of your Springboard. We're asked to find the exact value of the sine of 15 degrees. Now, whenever we're looking for exact values, that means we don't want to use our calculator because our calculator is going to give us an approximation, a decimal number. We want to use unit circle angles. And this is one way where the sum and difference identities can help us. I'm going to rewrite sine of 15 degrees as sine of 60 degrees minus 45 degrees. And I choose those two angles because they're both angles that are on the unit circle. And of course, when I subtract them, we get 15. There's a lot of other angles that you could have chosen. I'm going to just choose these two for this example. So now we're going to apply our difference identity for sine. And I'm just going to go right here and remind us what that identity looks like. It's in your foldable that we made in class. Sine of A minus B is equal to sine of angle A cosine of angle B minus sine of angle B times cosine of angle A. So we're going to use that identity. The 60 degrees is going to be our A, and the 45 degrees is going to be the B. So this is going to be equal to sine of 60 degrees times cosine of 45 degrees minus sine of 45 degrees times cosine of 60 degrees. Okay, so we've used our identity. The next step is going to be to plug in values from the unit circle. So sine of 60 degrees, that is the square root of 3 over 2. Cosine of 45 degrees is the square root of 2 over 2. Minus sine of 45 degrees, also square root of 2 over 2, times the cosine of 60 degrees, which is 1/2. So next step, I'm going to multiply these fractions. The square root of 3 times the square root of 2 would give me the square root of 6 over 2 times 2, which is 4. So that first product gives me square root of 6 over 4. Minus the square root of 2 times 1 would be the square root of 2 over 2 times 2, which again is 4. And so we have this answer, or since we do have a common denominator, we could combine those together into one fraction, square root of 6 minus the square root of 2 over 4. Let's look at another example of ways we might use these sum and difference identities. Here in example B, it says let alpha, this letter that's the Greek letter alpha, and sometimes we use that to represent angles. Let alpha be an angle on the interval 0 to 90 degrees, and beta, another Greek letter, be an angle on the interval negative 90 to 0. Cosine alpha equals 3/5, sine beta equals negative 5/13, and we want to find cosine alpha plus beta. Okay, so that's a lot of information. I want to start there at the end with what we need to find. We need to find cosine of alpha plus beta. And let's just remember from our foldable what this identity says. It says that cosine alpha plus beta is equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Okay, so in order to find our answer, I need to know all of these things. Well, I see that cosine alpha, that I already know. But the cosine of beta, looks like I do not know that. All that I know is the sine of beta. Sine of alpha, I do not know, but the sine of beta, that's the one that I do know that was given to us here. So I have some of the information that I need, but not all of it. The way that we're going to find the missing information is by using our reference triangles. So let's notice here that alpha is an angle on the interval 0 to 90 degrees, which means alpha is a quadrant 1 angle. So what I'm going to do down here is I'm going to draw a reference triangle in quadrant 1. So here's alpha. I know that cosine of alpha is equal to 3 over 5. It was given to me in the problem. And so I can use that information to label my triangle. If cosine alpha is 3 over 5, remember that's equal to x over r in a reference triangle. And so that means this side is 3 and my hypotenuse is 5. Now with that information, we can use Pythagorean Theorem to find the y side, which of course would be 4. It's a 3, 4, 5 right triangle. And now that I have that 4, I know that sine of alpha would have to be 4 over 5, which is y over r. So that gets me, I know cosine alpha, and now I know sine alpha. So I have two things, or the two alpha values that I need. We also have this sine beta, but we need to figure out cosine of beta. So we're going to do that reference triangle. Notice up here that beta is an angle on the interval negative 90 to 0. So that tells me that beta is in quadrant 4. Between negative 90 and 0, there's beta. We know that sine of beta is equal to negative 5 over 13. That was given to us in the problem. So I'm going to label those values on my triangle. This is y over r, which means my negative 5 goes on the y side, and the 13 is the hypotenuse, or the r. Using the Pythagorean Theorem, we can find the x side, and actually this is going to be 12, because 5, 12, 13, that's another Pythagorean triple. But if you didn't know the triple, you could do Pythagorean Theorem and find that value of 12. And now that we have that number, we know that the cosine of beta is going to be equal to x over r, or 12 over 13. And that is the last piece of information that we needed. Okay, so I paused there to kind of clean up our screen a little bit, wrote our values out to the side that we need here. So we're ready to substitute into our identity. Cosine of alpha plus beta is going to be equal to the cosine of alpha, which we're given is 3/5. The cosine of beta, we figured out that that was 12 over 13. Minus the sine of alpha, which we determined is 4 over 5, times the sine of beta, which they told us was negative 5 over 13. And so now all we need to do is simplify. We're going to multiply our fractions. 3 times 12 is 36, and 5 times 13 is 65. I've got a minus 4 times a negative 5, so that's going to become plus. 4 times 5 is 20, and 5 times 13 is 65. And then if we add those two things together, we get 66 over 65 as our final answer. This would be equal to cosine of alpha plus beta. Okay, actually I think I added incorrectly there. Let's fix that. 36 plus 20 is not 66, but 56. That's our final answer, 56 over 65. All right, let's look at one more example. We're going to do example C. In example C, we are given that sine of theta is equal to 1/4. Theta is between pi over 2 and pi, and we want to find the exact value of a few things, of cosine theta, sine 2 theta, cosine 2 theta, all of those things. Well, in order to do that, we're going to do a reference triangle again. I notice that theta is between pi over 2 and pi. that would mean theta is a quadrant 2 angle. So we're going to draw a reference triangle in quadrant 2. And so this angle would be theta. And we know that we're given that sine of theta is equal to 1 over 4. So sine is y over r, which means this side would be 1, and my hypotenuse is 4. So we need to solve for the x side down here. And I'm going to use the Pythagorean Theorem to do that. This is not a Pythagorean triple, so I'm actually going to do 4 squared minus 1 squared is going to equal x squared. And so 4 squared is 16 minus 1 is x squared. So x squared is equal to 15, and x would be the square root of 15. And since we are in quadrant 2, x is actually going to be the negative square root of 15 because x's are negative in quadrant 2. So I'm going to erase that work right there and just label negative square root of 15 on our triangle. So let's see, I think with that information we should be able to find everything we're asked for. First of all, cosine theta. Well, cosine theta is going to be x over r, and we just found the x. Negative, whoops, I didn't save room for my root, negative square root of 15 over the hypotenuse, which is 4. So that's our cosine of theta. Sine of 2 theta. Okay, now here, since I don't know exactly what theta is, I don't know what 2 theta is equal to, but I do have an identity. If you'll check your foldable on the double angle page, because this is a double angle, you're going to see that sine of 2 theta is equal to 2 sine theta times cosine theta. And we have both of these values, so we're going to plug in 2 times sine theta, which is 1/4, times cosine theta, whoops, which is negative square root of 15 over 4. And then if I multiply everything there on the top, we get, well, this 2, notice the 2 doesn't have a denominator. I'm just going to write it over 1. So 2 times 1 times negative square root of 15 is negative 2 square root of 15 over 1 times 4, which would be 16. And then that would reduce to negative square root of 15 over 8. So negative 15, square root of 15 over 8, that's going to be our sine 2 theta value. Finally, we need to find cosine of 2 theta. And if you look at your foldable on cosine of 2 theta, you'll notice we've got 3 different choices of things we could use here. I'm just going to use the first one, cosine squared theta minus sine squared theta. And we have learned that cosine theta is negative square root of 15 over 4. So negative square root of 15 over 4, that's cosine theta, but I need to square it, minus sine theta, which is 1/4, and I'm going to square that. If I square a negative number, it's going to turn out positive. If I square the square root of 15, I just get 15 over 4 squared would be 16. When you're squaring a fraction, you need to square the numerator and the denominator. Minus 1 squared is 1, and again 4 squared is 16. And 15 minus 1 would be 14 over 16, which of course would reduce to 7/8. And that was the last value we were asked for. So those are all the examples I'm going to work for you here. Next up here, this is going to be your assignment that we're going to work on in class.